So the last application of integrals that we're going to learn about right now has to do with arc length. And it's basically the idea of measuring something that is curved, which should kind of ring a bell from Calc 1, because in Calculus 1, we learned that a lot of things are kind of different if you are trying to work with curved functions, right? Things that aren't a straight line. And the goal here is, eventually what we're going to do is we want to measure, like, how far is this curved piece right there. That's the goal, this bit of arc. So from x is equal to 2 to maybe x is equal to 5, and maybe this function is, x minus 1 squared or something like that, right? But just a parabola shifted to the right by 1 unit, right? What would the length be there? And, again, a reason why is because a lot of times if you're an engineer or a designer, you're using computer programs to design things that are not just straight boxes and straight lines, things like that. And so, determining the length of a sidewalk, determining the length of a retaining wall, how much, concrete do you need to pour if you're building a garden and you need to lay down some soil or something like that, right? Or you're paving a road, right? These are all applications. If you're doing structural support, how much steel are you going to need to melt in order to create a curved beam? Whatever it is, being able to measure the length of something that's curved is going to be kind of interesting to us. But as you can kind of imagine, it's going to take a little bit of work. And the problem is that in order to measure the length of something, right, back in the day, what we used to do, if I just had 2 points, the best we could do is draw a straight line between them. And we could say, okay, the distance between 2 points, right, distance used to be given by the square root of x2 minus x1 squared plus y2 minus y1 squared, right? This is the best we could do. And in calculus speak, what that meant was, if we had these 2 points and we drew like a little hypotenuse between them, we might call this, using calculus terminology, some delta x, the change in x, right? That's what this used to be. And then maybe the other part we could call like delta y, some change in y, right? Good old delta y. And this is how you calculate distance, straight line distance, good old fashioned Pythagorean theorem, distance formula, however it is that you remember it. But kind of like I said, this obviously doesn't work for something curved. It's not the exact length. And so just like from calculus, what we do here is if you want to calculate distance, what you do is, instead of doing a whole bunch, the whole distance at once, is we kind of cut up this piece into a whole bunch of tiny sections, and we look at one tiny piece at a time. So like if I were to kind of zoom in here on this piece right here, okay, if I were to zoom in on that piece, that bit of this curved function no longer looks curved, right? If we're zooming in all the way between our little slice, we're thinking this is infinitely small now, right? So infinitely close, okay, a tiny slice. Now our line looks straight. It doesn't look curved anymore. And we can do the same thing where we can now use, again, the distance formula or the Pythagorean theorem, but now our change in y is no longer really big. It's really tiny. And we could call this side, our delta y, but it's not delta anymore. It's infinitely small, so we call it dy. And same thing on the other side, we have an infinitely small change in x. And so when it comes to arc length, I don't know if you all remember this, but way back in the day when we studied pre-calc 2, arc length was denoted with the letter s. So s is the letter that we use for arc length. Don't ask me why, I'm not sure. But S is for arc length, and so a tiny little arc length they refer to as ds. And so basically, what's the point I'm getting at is this process of using integration in the same way that I've been using for everything else, which is that if I want the total length, right? If I want the total length, well, we can get that by adding up a whole bunch of tiny arc lengths, right? And those tiny arc lengths we can summarize as just adding up all these ds's from like x is equal to 2 to x is equal to 5 or something like that. But what is tiny arc length? Well, using the Pythagorean theorem, hopefully it's not too bad. We can use the Pythagorean theorem and get that this is going to be, dx squared plus dy squared, all in the square root. That's not so bad. Again, like x is equal to 2, x is equal to 5, and we have a formula for arc length. This is it. Okay. Now, you would be totally right in saying, what the heck? I don't even understand how to integrate something like this. And I would be like, you're totally correct, right? Because normally we have integral of like a function with a dx at the end or a dy at the end. And here we don't have any of that. We have our dx's and dy's inside of a square root, which is a problem. We can't work with this. But, we're going to do some mathematical fudging and we're going to make it work. And so what I mean by that is that these bounds are in terms of x, which means I need a dx to be kind of somewhere out here. And so for no reason at all other than that I need one, I'm going to just kind of pop in a dx over dx at the end over here. And you might say, well, okay, sure, like I guess dx over dx, that's just 1, so I guess we can do this. But what I'm going to do that's interesting is the next part, which is I'm going to take the square root dx squared plus dy squared, and I'm going to separate this into, I'm going to put like 1 over dx here, and then I'm going to put times dx at the end. Now, before I go on to explaining what I'm going to do in the next part, I would like to remind you all that when I take the square root of something, like 9 times 2, for instance, that just becomes, 3 times the square root of 2. And normally we think about it going this way, where we pull the square, we pull the square root of 9 out and it becomes a 3. But imagine that I wanted to take this 3 and I wanted to shove it back inside the square root. In order to shove the 3 inside the square root, you have to square it, and then it can go back inside the square root, because 3 squared inside of a square root is the same thing as 3 alone on the outside of the square root. And the point that I'm trying to get at is I'm going to take this 1 over dx and I'm going to shove it inside of this square root, but I'm going to do it carefully by, I have to square it first. So I'll have dx squared plus dy squared. But I'm going to put all that inside of parentheses. I'm going to put this inside its own parentheses, and I'm going to put 1 over dx squared right there on the inside of the square root, and then I'm going to leave the yellow dx on the outside. Now, what's going to happen here? Well, 1 over dx squared, that's just going to be as if I was just squaring the bottom, so I'm just going to put like that squared on the bottom down there, if that's okay. And all I'm going to do is I'm going to distribute this sucker in, and this is what we're going to get. We're going to get the integral of the square root of, I have dx squared over dx squared plus dy squared over dx squared with a dx on the outside. And hopefully, we kind of notice very quickly that we get, this is an integral of the square root of 1 plus, this is just dy dx squared, right? Dy dx squared, or derivative squared with a dx on the outside. And now this formula here is usable. This is a usable formula. It's usable because, number one, now we have a function times dx that I can integrate. And number two, dy dx is just the derivative with respect to x. And this is it. This is our arc length formula. This is it. Arc length formula. And if you're ever wondering, do I ever memorize this formula? The answer is no, I never memorize it. Every single time I just tell myself, look, I'm adding up a whole bunch of tiny arc lengths. Adding up tiny arc lengths, that's square root dx squared plus dy squared. And then I remember that I need to get things in terms of dx, so I put dx over dx, and then I remember to do the fancy little math to get it on the inside. So if you want to memorize this, that's cool, but there's going to be, some various applications where maybe memorizing it isn't so, useful. I think the process is kind of what's more important. But let me show you an example. So if I said, let's set up the arc length, right? The arc length for y equals x squared from x equals 0 to x is equal to 3. All right, so using this formula, the first thing that I need is I need to know what dy dx is. So dy dx is famous for being 2x, I guess, in this case. And so our integral setup is going to be from 0 to 3, square root 1 plus 2x quantity squared with a dx on the outside, and this would be my setup. Now, we can't integrate this particular one that I just made yet. We need a technique that's coming in a couple of weeks, or rather, I guess, in 1 week. But I think, a lot of these questions that you're going to see on the homework are either setups or they're going to have functions that you do know how to integrate. So this is doing it with things in terms of x and y. The worst case scenario that you might see is maybe something that's parameterized. So maybe one other sort of function you might see is, to find the arc length of the function given by, x of t is equal to like t squared minus t, and y of t is equal to e to the t for, t goes from like 0 to 4 or something like that, right? So this is a parameterized curve, right? It might look something like this from 0 to 4. We don't know what it looks like. And so the question is, what is our formula now? Because our formula before that we came up with, it has things in terms of x, and that's fine, but we need to get stuff that's in terms of t, especially because we can't really get rid of these parameters so easily, right? We won't be able to just solve for t and plug one into the other one and figure it out. It won't be so easy. So, what is the arc length formula involving t? Well, we're going to stick with the same idea that we're going to add up a whole bunch of tiny arc lengths, and this thing stemmed from the idea that we were adding up all the square root dx squared plus dy squared. And just like before, we're going to use this same trick, which is like, look, before I wanted to integrate with respect to x, so I multiplied by dx over dx. But here, everything is in terms of t, right? My curve is given to me in terms of t, so I'm going to introduce a dt over dt. And hopefully we can kind of see the same trick happening, which is I'm going to put a big square root. I'm going to put that dx squared plus dy squared, squared there. And I'm going to pop in a 1 over dt squared on the inside. And I'm going to leave another dt on the outside. And this is going to distribute in and give us an integral formula, square root dx squared over dt squared plus dy squared over dt squared with a dt on the outside. And if you want to tidy this up, you can write this as dx dt all squared plus dy dt all squared dt. And this will be our arc length formula in terms of something that's parameterized, like in terms of t or theta or bob or whatever it is that they give us. So in this given example, we'd set up our integral. But the first thing we need to know what dx dt is. So dx dt here is 2t minus 1. And then we need to know what dy dt is. And since we just had e to the t, it's just going to be e to the t. And so we know our bounds are from t is 0 to 4. We pop a square root, and we just plug things in. So we're going to have 2t minus 1 squared plus e to the t squared dt. And this would be our setup for calculating the arc length in this particular problem. So not too bad in both cases. Hopefully it makes a lot of sense, and you're kind of following the same trend, which is whether it's probability, work, area, volume, or arc length. The goal is just we take these big unmanageable problems and we cut them down to these really small, infinitely tiny levels, and then all of a sudden using integrals, adding up a whole bunch of tiny pieces gives us the final result that we are looking for. So that's going to do it for right now. I think that's enough applications to get us through the homework. So email me, post in the discussions if you have questions. And other than that, I will catch you all on Tuesday.